talking about solids, liquids, and gases in chapter 7, section 7.1 through 7.6 in this video. We'll start with this table, just outlining the 3 states of matter. You should be very familiar with these so far, but look at this table and I want you to highlight a couple of things. We're going to look at the arrangement of particles. So think about how far particles are apart. The difference in gas and liquid is a lot of space between the particles versus the difference in between liquid and solid is not as much. Then I also want you to think about the interaction between particles. Now, we assume that gases have no interaction. This is an assumption that we have to make in order for the math to work. It's not true that gases have no interaction for all gases. Some gases don't have any interaction or very light interaction, but we have to make an assumption here that they have no interaction between particles. We'll talk about interactions between particles at the end of this chapter, so just keep this in mind as a big difference in between the 3 different states of matter. So here are some images. I would love this image to have, let me just change this. This image should really, see if I can make this bigger. This image should really look like this. Oops, let me keep the N2 and the O2. I think maybe we'll keep that. This one. So this image should not have as many particles in it because the distance between particles is so great that if you were to kind of put it on the same scale of the solids and the liquids here, then you would actually see only one particle. You would not even see the other particles. So I'll just do this to show this is N2. But there would only be one particle. And if there are 2 particles, it's because they're like about to collide and then they're gone again. And so the space between the particles is really, really, really great in gases. And so this is a little bit better of a picture in your head than the previous one. So thinking a couple of things about the kinetic energy of the particles, gas particles are moving way faster, liquid particles are moving slower, and solid particles are still moving, but they're moving very, very, very slow. They're kind of vibrating. And then the strength of interactions between the particles, we can clearly see very strong interactions with solids because we form these crystal structures, very strong interactions with liquids because they're very close together, and very weak interactions with solids because they're very far apart. So we have to do this theory for the math I'm about to show you to work. So kinetic molecular theory is basically just the movement, so energy of movement, molecules, we're thinking about particles and molecules, and theory. So theory is a model for how things work in real life, and theories are ways for us to explain what we see in real life. So a couple of things we have to assume under the kinetic molecular theory, we'll also call this KMT, is the gas particles are moving randomly and rapidly. So they're constant random motion. Gas particles are very small. Their volume, we assume, is actually negligible or close to 0, where V is volume. We assume the volume of the particles is around 0 because the space around the particles is so much bigger than the space of the actual particle that we just can consider the particles to take up no space. This is not necessarily true. We know the particles take up space because they are matter. They have mass, they take up space. And so the particles are matter. They have volume, but we assume their volume is so small compared to the volume of the particle, the volume of the space between the particles, that we just consider the volume of the particles as 0. Remember, we did the same thing for electrons, right? We assume electrons have a mass of 0. Even though they do have a mass, just in comparison to protons and neutrons, it's very, very small. It's like the volume of an elephant compared to the volume of a fly. It's not, if a fly lands on the elephant, it's not really going to change the mass of the elephant or the volume of the elephant, right? Because it's so much smaller than the elephant. Gas particles exert no attractive forces on each other, and so this is an assumption that we make. This is not necessarily true. There are some gases that do have attractive forces with each other, and we'll talk more about these attractive forces in the end of this unit. But keep that in mind that we are assuming that they have no attractive forces on each other. These 2 things are assumptions we have to make for the math I'm going to show you to work. We do have some math equations if you're interested with these assumptions removed so that the volume matters and the attractive force matter in the math, but we're not going to get into the math for that in this class. And then the kinetic energy of the gas particles is increasing with increasing temperature. This is a direct proportionality if you're in unit of Kelvin for your temperature. In Celsius, this is not a direct proportionality. So you'll find that in all of the math we do with gases, we use Kelvin for a couple of reasons, but one of the reasons being that temperature is a direct relationship with kinetic energy, which is the energy of motion. So the faster, the higher the temperature, the faster my particles are moving. When gas particles collide with each other, they rebound and travel in new directions. We call this elastic collisions. And so they collide like billiard balls. They don't stick together. That's what basically we're talking about there. So if we simplified real life a little bit here into this theory so that we can then take these things and do math with it, because if they stick together when they collide, if they attract each other, if they take up a lot of space, then this makes the math a lot more muddy. And so what I'm going to show you are math equations that if the gases are essentially doing all of these things, they would behave by these formulas. We're going to talk a lot about pressure, and I want to make sure you understand what pressure is. So pressure is the collisions within the walls of the container, so the exerting of pressure. So if you kind of press down on your desk or press down on a wall, you're putting pressure on that, right? It's the force over area. So if you've ever worn high heels or anything, you understand pressure. If you're standing on your tiptoes or you are walking around, or even just like if you've ever done like a handstand or anything like that, like even like a plank position, right? If you lay on the floor, you don't feel the force of your body as much because there's a large area. This is how people can lay on like a bed of nails, right? The force of your body's pulling down on gravity is spread out through a large area. But if you come up onto your toes and your hands, like in a plank position, you start to feel strain in your wrists maybe, or in your toes. You feel that force because you have a smaller area, so the pressure increases. And so these are things that you experience in real life. You understand what pressure is. Like tire pressure, for example, can be something that you think of. There are lots of different pressure units. That's because everybody who's done anything in chemistry gases decided that they wanted to have their own way of measuring pressure. And so we have a couple of ways to measure pressure. This is millimeters of mercury. So mm is what you're familiar with, millimeters, and mercury is the metal. This is actually the liquid metal, and we use it in barometers. And so this is how we measure air pressure sometimes in millimeters of mercury, because it's literally how high does the barometer read? Like how many millimeters does the barometer go up, a mercury barometer? Torr is another measurement. PSI, pounds per square inch. This is maybe what you're familiar with if you've ever filled up air pressure on a tire at all. You've seen PSI. And then pascals is named after some person, Pascal. And so we will be using these things. I think on your equation sheet, you have some of these conversions. These are just conversion factors. So we're just going to use them as conversion factors. You don't need to memorize them. I'll give them to you. But if you do see maybe that we need to do a conversion between any of these units to atmospheres or ATM, there's also a unit called bar, which is used. But you'll find that we do a lot of our math in atmospheres. We also will do some math probably in millimeters of mercury or torr. We don't, you may see pascals or kilopascals, which we can just turn quickly using the SI prefixes there. So these are just some conversions. Again, you don't have to memorize these. They will be given to you on your equation sheet. But just keep in mind, we will be doing some conversions with the math today. Boyle's law is our first law we're going to talk about. And in class, we're going to kind of skip over these individual laws because I think it's more important for you to learn the relationships between these things. Basically, Boyle's law is talking about pressure and volume. And so if you keep it equal to a constant, if one goes up, the other has to go down. And so because they're inversely related. And so you need to know this. And if you think about a balloon, you kind of already know this. If you decrease the size of the balloon, so if I make myself a little balloon here. So if I have a balloon and I think about squishing it down, right? The pressure inside the balloon is going to be greater when it's squished. So decrease volume, we're going to increase pressure. See how it's a inversely related thing. P is for pressure, V is for volume here. So think about this is a cylinder with like a piston pressing down. So if we compress the gas, we increase the pressure. Right? So if the volume is smaller, the pressure goes up. And then we can explain by this equation initial conditions and new conditions. So if this was my old relationship here, this would be my new relationship here, and they are going to equal each other because they equal a constant. So they're always, if you multiply pressure and volume in any situation, it will be the same as that same pressure volume in a different situation, assuming other variables are kept the same. I will let you work through this. So here, we'll actually talk about these examples in class a little bit. But if this is your formula, P1 V1 equals P2 V2, can you solve for V2? So you can pause the video and work through this. So we can rearrange our algebra first. I totally think that you should do that, especially if you know that algebra is not your strong suit. Let's rearrange our variables first, and then we'll plug our numbers in. And make sure that your units are going to cancel. So for example, this one was milliliters and this one were liters. We have to do some kind of conversion to make that work. And then we'll just plug and check. This doesn't have to be that difficult. Real application of Boyle's law, which we'll talk about in class, inhaling. And so when you inhale, you are making more space. So we're increasing the volume. The pressure inside of our lungs goes down. And so the outside air pressure is higher than the inside air pressure. And so the outside air goes into our lungs to fill our lungs, to make the pressure the same again. And so that expands our lungs. It fills our lungs with air, essentially. So when you're breathing, it's not you sucking in air, it's you making your lungs bigger, the pressure decreasing inside your lungs, the outside air pressure pushing air in to equalize pressure. That's really like, it's like air is choking us essentially when we're breathing, not us sucking in air, even though that's kind of what it feels like. And then when we exhale, we contract our diaphragm. So we have high pressure inside our lungs, and that pressure is greater than the pressure outside. So pressure, it always moves from higher to lower pressure. So in high pressure inside, lower pressure outside, air is going to go out to equalize pressure. So that's how exhaling works. Charles's law is the next one. Again, you don't have to memorize the names of these laws, but it is a direct proportion. So it is going to be V over T is your constant. We'll talk about the formula in a second, but it's direct. So if one goes up, the other also goes up. Volume and temperature is what we're looking at here. And so if you decrease your volume, sorry, if you increase your volume, you increase your temperature. And so this is the relationship here. V1 over T1 equals V2 over T2. Again, because they both equal a constant K, then they can equal each other. And so this is how wind currents really work. So warm air rises and the density heated air expands. So that's why if we increase the temperature, we also increase the volume. And then if we increase the volume, the density decreases, so that makes it rise up. And so cool air is more dense and it kind of moves in to take the space of the warm air. Gay-Lussac's law is pressure and temperature, and you know this one as well. If you increase temperature, you probably also increase pressure. So example, in the winter, your tire pressure that may look lower and it may read as lower, so you may get like a pressure sensor light go off in your car because the temperature is low. If you drive around in your car for a while and increase that temperature, your pressure will increase a little bit. So you should not be filling up your tires air pressure in cold weather until you've driven around for a minute on that, because you could overinflate your tires. And so here, if we increase our temperature, it's gonna increase our pressure. This is assuming the volume is the same for both. Like our tire, the volume of the container is the same size. And so here is our relationship. And again, you can do any sort of calculations with this. We like to combine all of these three into something called the combined gas law. I'm going to show you a super combined gas law in class, where we actually include the next one in as well. But we can combine these, and so we can change pressure, volume, and temperature and find new conditions for this. Or we can say we can memorize a combined gas law, and then if we don't use temperature, for example, just remove it and have only one of those laws. So here is a little table for these laws. We're going to add one more law, and then I'm going to provide you with a super combined gas law, which is Avogadro's law. So Avogadro's law is volume versus number of moles. The unit or the variable for moles is N, not M, because M is for mass. So we had to have another letter, and they picked N for this, like number of something. So that would be an amount. And so number of moles. If you increase the number of moles, like you blow in a balloon, it makes the volume bigger, right? This is assuming the pressure is constant. And so again, we have a relationship here. And then for your super combined gas law, let me just put that in here. Super combined gas law. I like to call it PV-teeny. So P1, V1, T1, N1, PV-teeny. Here. This would be my super combined gas law. I think it's better just to know this one versus all four of those others, because if we're working on a problem and they tell me the temperature is constant or they don't talk about temperature, I can just erase temperature. And if they tell me, hey, well, moles are constant or they don't talk about moles, we just erase moles. And now we're just dealing with this one. Or we can say they told me the pressure was constant, it's the same. And where they don't say anything about pressure. And then maybe they said the temperature is constant. And so they don't talk about temperature. And so now we're dealing with what's left over. And so I think if you look at this one, if we work on this as like our main one, we don't have to worry about each individual gas law. We can have a quick don't have to do this algebra math if we're at standard temperature and pressure. So we call this STP, and STP is 1 atmosphere and 0 Celsius. And so I like to remember 1 and 0 for STP because it's easier than 760 and 273 for Kelvin. So 1 mole of gas is a volume of 22.4 liters. At STP, we call this the standard molar volume. And so you can say 1 mole of a gas at STP equals 22.4 liters of that gas, also at STP. So maybe I should just write, let's do this instead. Let's write 1 mole gas equals 22.4 liters of gas. You gotta make sure this is gas. I know some of you will really want to use this for other conversions or other substances like liquids and aqueous stuff, but you gotta make sure this is only talking about gases specifically at standard temperature and pressure. And now we have a quick conversion. We don't have to do any sort of math with any of this stuff. We can just do a quick little conversion factor to figure out the difference between volume and moles. And so Avogadro's law is where we get Avogadro's number from, or where Avogadro got Avogadro's number from, because even though they're at different masses, they both contain the same number of particles. And so that's where we get the mole from, essentially. So here's an example for Avogadro's law. Convert moles of gas to volume at STP. So remember the conversion is 1 mole equals 22.4 liters. And so I bet you could do this really quickly. So pause the video and go through that. So we can use a conversion factor, right? Either one. And then if we cancel out our liters, we get moles. Imagine that I could give you grams or ask for grams, or we could do a mole ratio next, right? Or we could do Avogadro's number to find number of atoms or molecules. And so there's a bunch of stuff that we could do with this. 2 more left, so hang in there with me. The ideal gas law is next. So the ideal gas law actually comes from PV-teeny. So PV, or they are influenced by each other. So PV-teeny, remember all of these laws were a constant. So let's call that constant R. Now, if we rearrange this, we actually can get this. And so the ideal gas law shows relationships between all of these things. So 2 things on the same side have an inverse relationship, like this one goes up, this one goes down. If they're on opposite sides, they have a direct relationship. And then we have this constant R. This is the constant here. We're not going to really be using the MMHG one. We're just going to be using the ATM one. But this constant makes things work. It makes the math. And so if we know that one side of our PV-teeny is equal to a constant R, and then we could actually rearrange this into this, then they're kind of the same law. It's just if we're talking about like initial conditions and final conditions, like changing two different things, or everything, we're not changing anything, we just want to know a piece of this. So these are the two laws we're going to talk about, and we'll talk in class about how to use them, how do you know when to use them, but you're going to be using this R. This is the units of R. We do not plug numbers in for units. We plug numbers in for variables. So the variable for R is this. So when you see R, you actually will plug all of this in here. And if we notice here with our units, all the units have to match the units of R. So temperature must be in Kelvin, N must be in moles, pressure must be in ATM, and liters must be in, volume must be in liters here for this one to work. For the previous one, we'll talk about this in class too, but all your units have to be in certain units. Pressure and volume can be any units as long as it's the same on both sides. For the previous one, that's this guy. So this one here, I'll just write it here in the notes for you. So P and V units must match. So for example, P1 is ATM, so P2 must be ATM. V1 could be milliliters as long as V2 is also milliliters, so they match on each side. T must be in Kelvin. We have to be in Kelvin because Celsius of 0 is a very real thing. Can we divide by 0? No. So we need to make sure that we are using units that will actually work. And then N must be in moles. So you might be given mass, but you must convert to moles. For combined or ideal gas law, all units must match units of R. And we're going to be using this R. So can you look up other R's? Sure. We won't be using this guy. And again, you don't have to memorize this. This is provided to you on your equation sheet, I believe. So let's see how we could solve a problem like this. So how many moles are contained in a typical human breath that takes 0.5 liters of air, 1 ATM, and 37 degrees C? And so if we identify all of these things, we're going to list them out. Again, we'll do this practice in class, but they give us these three things and they ask us for this. If you see they give you 1P, 1V, 1T, and 1N, you're going to use PIV-NERT, ideal gas law. We're not using PV-TINI because we don't have two of each. So if we go back to an example where we use the PV-TINI, let's see, here is our example here. See how they gave us a volume and a pressure and then a new volume? So there's two volumes here. So we have to have two volumes. This would not be PV equals nRT because we don't have a T, we don't have an N, right? We're not asked for those things. So looking at this problem, see if you can figure out how to plug these in. Check your units. If R is equal to 0.08206 liters times atmospheres over moles times Kelvin, we got to make sure all of our units match. So make all of your units match. For Celsius to Kelvin, remember the Kelvin is 0 Celsius plus 273. That's going to be your conversion factor. You can say 273.15. I'm not sure what's on your equation sheet. We'll have to look at that in class, but pause and see if you can work this out. We're solving for N. All right, so we need to make sure we have Kelvin. Sig figs tell us we're going to go all the way to the ones place here and not any further. And then we have our R, and everything is in units of R otherwise. So liters, atmospheres, moles, Kelvin, so we're good. And then we can solve for N, and then we can plug everything in. Notice that the units cancel out if you have everything set up correctly, and then we get an answer. Last little bit here, hang in there with me, is Dalton's law. So Dalton's law is really simple. It says total pressure is all the partial pressures of a mixture combined. So let's say we have a mixture of air. It has oxygen, it's got nitrogen, it's got argon. The total pressure of the air is the pressure of the oxygen and the pressure of the nitrogen and the pressure of the argon. This is very simple, right? The total is the sum of the parts. You know that's what a total means. And so here's an example. If we have nitrogen, oxygen, carbon dioxide, and water in a sample of exhaled air, what's the total pressure? We just add them up. Make sure they're in the same units. That's all we can say about this one. So make sure all units are the same. So if you've got one in ATM, you've got one in torr, you've got one in millimeters of mercury, they all have to be the same unit. Otherwise, you're just going to add them all up, or you subtract them if you're given the total and you're asked for a part, right? So this is not that difficult. All right, that is it for this video. We'll see you later.